Hello. Let me just check if we are live. Yeah, we are live. Okay. Superb. Superb. Today we are working on a system design question for distributed view formula. Let me just share this screen. We'll get started in 1 or 2 minutes. Yeah, I think I'm audible now. Correct. Good. Awesome. Okay, we can start. Okay, so I'm following this hellointerview.com website for system design preparation. I will be solving distributed rate limiter system design question. So yes, I'm following this hellointerview.com. Basically, it has a nice dashboard and structured content for system design. That is why. So yeah, today like I've just started with my system design preparation. That is why this is one of the beginner questions, and it's also one of the most asked questions in system design interviews. That is why. So okay, let's start working on a system. So before we dive into designing a rate limiter, we first need to understand what a rate limiter is, right? So a rate limiter is basically a component, or a service in your system which would limit the number of requests to a particular resource for a particular time window. Okay, so this time window thing is very important. Basically, we are somewhere we are trying to say that a particular user, or let's say a particular client, cannot send more than n number of requests to your API within 1 minute, right? Because we have to implement a rate limiter. Now why do we want to implement rate limiter? uh, few points could be. One is to avoid denial of service attacks. If someone uses a script or a bot to continuously send a request to your APIs, and try to abuse the APIs, then we have to limit that. So we can do that by implementing rate limiter. Another option is we have to prevent our servers from being overloaded. So that is also one point. Another point is to reduce the API cost, because if you are doing some DB transactions or whatever, like we don't want too much request to our API within a small period of time. That is why. Okay, so that is the basic of why rate limiter is required. I've gone through this chapter, design rate limiter, in Alex. This is the Alex user book. So if you want, you can also go through this design a rate limiter. Um, so yeah, here we can go through what are the benefits of using a rate limiter. So we can prevent resource starvation caused by denial of service. We can reduce our cost. If we have if we are limiting the number of requests, we can have fewer servers, correct? And preventing servers from being overloaded. So these are the main points. I think we can start with this. design. Just important point that I have 3 years of experience. That is why I'm going with a mid-level uh, level. Okay, so yeah, let's start. Okay, so they have provided us the functional requirements. So we'll go through each of the functional requirements. So first is the system should identify clients by user ID, IP address, or API key to apply appropriate limits. Correct. So if you are implementing, rate limiter on HTTP request, we need to be able to identify a client, and we need to be able to figure out the number of requests a client is sending. So there should be a identifiable part for a client. Now here they have provided certain metrics. We can either identify a client via its user ID. User ID might be applicable for a logged in user, IP address for an anonymous user, or API key for an authenticated user, something like that. Okay. Second functional requirement is the system should limit HTTP request based on configurable rules. Correct, because every system might have different requirements for this. How many basically uh, what are the rules, right? Basically, are we allowing 100 requests per minute, or 5 requests per minute, something like that? Or basically, even in a particular system, for different services we may have different limits. For a service, for maybe post service, we are saying that you can allow 2 posts per minute, but for a comments service, let's say we are allowing 10 or 20 comments per minute. So these rules need to be configurable, and they can be different based on the system. Okay. Third is this is an important point, because if the limits are exceeded, we want the system should be able to reject the request. And when we reject the request, go for if resources if number of requests are exceeded, we provide this resource code. Yeah, status code, basically 429. Okay, and we can include some helpful headers which would mention about that, which would tell the user that they are rate limited. Okay. The scale of the system also they have provided us the scale. That is, scale is the expected scale of the system is 1 million RPS across 10 million daily active users. So RPS basically means request per second. So that is given for us to have a basic idea that our design should take these number of requests into consideration. Okay, if we are expecting 1 million requests, we have to build a system which can sustain 1 million requests. Okay, so let's move on to the next point. Next. Okay. Okay. Right, so basically Hello Interview has provided its delivery framework. So we can go through the delivery framework. We can go through the delivery framework. So I've already gone through the delivery framework. Basically, one of first points is gathering the requirements. So requirements mean both the functional and non-functional requirements. Then we have core entities. We want to identify the core entities of the system. Then API requirements, if any, and then the HLD, and then the deep dive. So you can go through the delivery framework. It is available on the Hello Interview site. Okay, let's go ahead. Okay, so now first question, basically the functional requirements have already been given to us. So now we are concerned about the non-functional requirements. What are the non-functional requirements? Okay, so we can open a whiteboard and we can get started. So here they have provided us the whiteboard. So here they have already written the functional requirements. So non-functional requirements, if you go through the delivery framework provided in Hello Interview, are mainly stuff which are like the system can lines like the system should be able to, or the system can perform something. So these are mainly related to so first one major important part which you have to handle in non-functional requirements, it is the cap theorem. Okay, so out of consistency and availability, you have to figure out what is more important. So for our design, I would say the system should be highly available, right? Basically, see, rate limiter is probably, it acts like a gate. If rate limiter is allowing something, then only the request would reach our API. So our rate limiter should be highly available. We cannot, compromise on this. It should be highly available. Otherwise, our API responses will become very slow, right? So the system should be highly available, and so highly available, and when we are saying highly available, we can also say eventual consistency, because highly available means that system would be eventually consistent. So this is coming from the cap theorem. Okay. Second important non-functional requirement is, so if you go through the delivery framework, they have provided a list of some of the metrics which you can take care of when you are writing the non-functional requirements. So one are taken care of. Second is latency. So in our system, we expect low latency, correct? But how low? I think less than 10 ms is good. We expect less than 10 ms latency for the rate limiter. Okay, so latency, the system should have low latency. Okay, and let's say less than 5 ms is also good. Okay, then we are saying other than that, they have already given us the scale. So scalability is also one important point we can add in non-functional requirements. Again, keep in mind that let's only have 3 functional requirements and 3 non-functional requirements. We can have more, obviously, but for the sake of interviews, it's better to keep the ball in your court to have minimal stuff which we can work through during our 1 hour interview. Okay, so let's say the system should handle 1 million RPS, which they have already provided us here. Okay, across 10 million DAU, whatever they have provided, the same thing I'm giving here. These are the non-functional requirements. It should be highly available and eventually consistent. Okay, let's get feedback on our answer. I believe this is good. This is good enough, right? So this is a great answer. That's good. Consider quantifying your availability requirement to make it more measurable. Okay, you might want to add one more requirement about the accuracy of fairness. Okay, let's see, a sample answer is something like that. Okay, I think we can continue. We can go to the next question. Okay, the next question is, what are the core entities? Okay, what are the core entities? So core entities basically mean what are the stuff our APIs will work on. That is a good way to think about the entities. So if we write some API for this system, it would work on what basis, or on what resources. So first and foremost, if you can identify, it has to be client ID. This client ID would mean either the user ID, basically something by which we can identify a request is belonging to a particular user, correct? So either it could be the user ID, or it could be the IP address, or it could be the API token, correct? Let's go to core entities. So we have client ID. Another can be request, correct? Request, because ultimately we are counting the request or tracking the request, correct? So request is one entity. Other than that, so for core entities, we can go through this functional and non-functional requirements, which it would give us an idea. Right, so rules, configurable rules. So rate limiting rules are another core entity, because we would define the rules somewhere in the system, correct? So yes, I believe these are the core entities. We can continue. I think get feedback. Okay. Yeah, this is totally fine. This is good. Next question. What is the interface of the system? In other words, what are the functions that the system exposes? Okay, what are the functions that the system exposes? What are the functions that the system exposes? So basically, so somewhere we would have an API which would consist of the client ID. So input would be something like client ID, and output would be something like is allowed. Correct? Basically, we would check against the client ID if the client is allowed to log in or not. Sorry, allowed to, the request is valid or not. Let's say valid. Okay, so this is a boolean. Client ID can be anything actually. So output would be this. Yeah, I think this is fine. Let's see. Is it good? You correctly identified client ID as an input and allowed a boolean response. Missing rule ID as an okay. Yeah, basically we would also depend on the rule ID, right? The algorithm we have to implement. Correct. And the rule ID is basically that's right. Rule ID is basically whether we are allowing 5 requests per hour or something. So that obviously we need as an input. Correct. My bad. Remaining count. Okay, so these are basically the headers which you can provide. Try again. So like in output we can provide the headers, right? The rate limiting headers and stuff. Your output is missing two important components: the remaining count of allowed request and the reset time. These are crucial. Okay, let it be. I will not change my answer. Let's continue to the next question. Okay, where should the rate limiter be placed in your overall system? Draw a simple diagram and explain how it answers the question. Okay. So where should the rate limiter be placed? So basically what my idea is that we have a client system. Sorry. We have a client system. Let me make it Excel, right? And we would have the API servers. So let's just assume we have multiple servers, right? Let's say we have microservices architecture. So API server 1, API server 2, and API server 3. And API server 3. Okay. So this is good. And now the question is, where should the rate limiter be placed? So essentially, if you think, we have multiple approaches. We have multiple ways or multiple places where the limiter can be placed. First is, which I think is, inside the servers, inside the web servers or application servers. So, but here, suppose if we have, n number of servers, so we would have a rate limiter inside each of the server, and inside the server it would do the calculation and accordingly allow the request to the actual API endpoints, or it would return 429 code to the client. So one is inside the application servers. Another is we can have a different an entire different service, or let's say separate rate limiter service, as a middleware. Something like, we can have something like, let's say in here we can have a rate limiter. This is a separate service entirely. Third option, and which is basically the best option, that is placing it inside API gateway. So we can say rate limiter inside API gateway. This is actually the best option. Okay, because see, if we have a separate, basically this is a very, bad approach. If we keep track of, request rate limiter inside each servers, it is not an accepted approach. Okay, because let's say, if we have some rate limits, then every server would only be, every server will only have idea about the rate, about the count or the track of user request for itself, correct? So we won't have a global, counter for the request coming from each client. That is why dedicated service is a good option. We can go via that option, but API gateway is usually the, more accepted solution, where we have API gateway and we would place our rate limiter middleware inside it. Let's say. So this is the rate limiter middleware. So we would place it inside the API gateway, because anyways all the connections, all the requests would come to the API gateway. So this is a very, clean way of handling your rate limiter. So yeah, I think this is good. This approach, let me just write, will not consider. We shouldn't consider this approach. We should not consider this approach, since if we maintain counters per application server, we won't have global count per user ID, and that might lead to misleading calculations, obviously. Separate rate limiter service, I'm unable to think of a disadvantage. Suppose if we have a request, okay, right, if we have, suppose if it is a separate service, say every request would come to the API gateway, it would then go to the rate limiter. If allowed, then it would go to the, API servers. So if you think we are adding extra network latency, so this might add extra network latency. That is why we should go with rate limiter inside the API gateway. So it is present inside the API gateway. It is a nice approach, right? Because anyways, all the requests would come to our API gateway to be able to, map it or route it to the different API servers. So we can go with this approach. Let's say, okay, let me just place it inside. Let me draw the necessary arrows in here. Give me a minute. Yeah. Another arrow would be from here. Yeah. Or I could just, I could also show just one server for the API servers, but anyways. Right. So yeah, this is good. Okay. We have placed the client. Yeah, I think this is good. Let's see. Yeah, this is perfect. Recognize the limitation of in-application rate limiting. Correct. Okay, so let's move on to the next question, which is, what rate limiting algorithm would you use and why? Okay. So basically, there are multiple algorithms. There are 5 main rate limiting algorithms. Okay. So, the names are like token bucket, leaky bucket, sliding window counter, sliding window log, and fixed window counter. Out of which fixed window counter is the worst. And a good or optimized algorithm is token bucket algorithm, and also that is the algorithm I'm very much familiar with, so I would try to use that. So we have multiple algorithms. We have multiple rate limiting algorithms. For the sake of this problem, we can choose the token bucket algorithm. I'm not sure if I have to explain the algorithm here. Let me see. Draw symbol diagram. Okay, would you use and why? Okay, I'll have to explain the why, right? So why is token bucket algorithm? Token bucket algorithm maintains a bucket for the number of requests allowed and a refiller which and a refill rate which keeps on filling up the bucket. If a client request comes, or basically when a client request comes, when a client request comes up, we try to the algorithm checks if we have greater than, or like, greater than zero number of tokens available, or let's say just one. If we have at least one token available, we allow the request. Otherwise, we invalidate it. Also, if during refilling the the bucket is already full, the tokens are overflow. Apart from that, why should we use it? It is easy to implement and is memory efficient. Okay, so that is why we can use it. Other than that, it can also handle a burst of traffic. It can handle traffic burst, let's say. Okay, yeah, I think. But should we make any changes in the? Should we make any changes in here? I don't think so. Or okay, right. We have to make some changes because see, if we are using token bucket algorithm, basically we need a way, right? There should be a way, or there should be a system which will store this count for us, correct? Right? So we want to store each user's bucket. So to implement this algorithm, we want to store information of each user ID, or let's say client ID. Okay, this which is basically a bucket. Okay, and every bucket we would track the number of requests, current number of requests, or no, sorry. So we would track the current number of tokens, okay, available, and last timestamp when it was refilled. Okay, so that we can verify. And if you have to refill it, we either refill it, or otherwise if a request comes, we check if we have the tokens available. Okay, right. So okay, now where to store this information, right? So we can have multiple instances of API gateway as well. So again, if we store it inside a rate limiter, then we can have multiple instances of it. So a good way, or a practical solution for this, to have a global centralized state. So to have a global centralized system for storing these tokens, these buckets, these user buckets, would be using Redis. Now why Redis? Because Redis is in memory, Redis is fast, Redis is a good data store, and it can become our it can be helpful to store this data. So we can use Redis. So let me implement Redis here. We can add Redis over here. Let's say okay, I should be within this window. Can I just move all of it here? Yeah. So this is Redis. So we maintain Redis, which means now our rate limiter would keep talking to Redis, and Redis will also talk to our rate limiter. So yeah, something like this. Let's see. Good. Right. You didn't address atomicity concerns for bucket updates in a distributed environment. Right. When multiple API gateway instances access the same bucket simultaneously, we would have race conditions using Redis atomic operations or Lua scripts. Time to live. Okay, correct. So we need to take care of these steps as well. For now, I will not try this question again. But yes, we have to ensure that our operations are, atomic. Our operations need to be atomic, which means if we are getting in a distributed environment, two threads may try looking for a counter at the same time. So that would create some race condition. So to prevent that, we can use the Lua scripts, which are available in Reddit to ensure consistent updates. Uh, okay, I'm not going into the details for it. Okay, I think we can continue from here. So let's go to the next question. What will your system return to the user when their rate limit is exceeded? Switch to text mode. So if the rate limit is exceeded, we can we would send the 429 HTTP response code to our users. Yeah, right. We would send the 429 HTTP response code to our users, and I think this is good. And yeah, okay, we can also set up. We can also along with these rate limiting response headers. So we have some response headers, okay, available. So first is X rate limit, which would tell the limit if this is remaining, which would tell the remaining number of requests. Then we have a reset, and then we have a one more is there. I think retry something, retry after. So we have a retry after, which would tell the user that how much time they can retry the request. So yes, this is one thing which we can do. So should I add a, yes, I think we can add a for that. So invalid, or let's say rate limited request. So 429 response code and some of these headers which we would set. X rate limit remaining, X rate limit reset, and retry after. Right. Other than that, yeah, I think this is good. What will your system plan? Yeah. Okay, right. While you currently identified all the necessary headers, what each header means. Okay. Okay, we can provide the explanation as well. For now, let's continue. How do we scale to handle 1 million requests per second? How do we scale to handle 1 million requests per second? Okay, this is a good question. Okay. So basically, if you go through the capacity estimation or have earlier checked the capacity estimation stuff, you would know that Redis can handle some 100k. Let me switch to text mode. So Redis can handle some 100k operations per second, or let's say requests per second. Okay, to be able to support, or let's say handle 1 million requests per second, we would need multiple Redis instances, right? Basically we are horizontally scaling the Redis instances. Give me 1 minute. Give me 1 minute. I'm find something else. Give me 1 minute. Okay, we'll continue in 1 minute. Okay, okay, good. So yeah, okay, let's work on this. How do we handle to scale? How do we scale to handle 1 million requests per second, right? So okay, so right, so Redis can only handle some 100k thousand requests per second. And if we want to handle 1 million requests per second, obviously we can come to this conclusion that we would need to have multiple we would need multiple Redis instances. Okay, so uh, mathematically we can have 10 Redis instances, right? We have 100k and we want to support 1 million requests, we can go with this. Now again, we obviously horizontal scaling is possible, but with horizontal scaling we get one major issue, which is how to distribute the work between all the servers, correct? And obviously one of the most possible solutions for it is consistent hashing. So we would use consistent hashing to distribute the work across these instances. Okay, so what we can do is for for so again, initially we decided, right, that we can have user ID or client IP. Based on that, we would maintain the buckets. So for user ID, for basically for clients, we can either hash the user ID, or the IP address or the API token, and use that hash in the consistent hashing, right? So that can help us in distributing the request. So also this would ensure that the requests from the same client are going to the same server, are going to the same Redis instance. Okay, so yes, we can have multiple instances of Redis. Should I create multiple instances? I think I can, but let me do one thing from the inside box. Yeah, right. Right. So this way we are, saying that we have multiple instances. I mean, the diagram is not really good, but it would convey, our point is now spoken. I think so. Yeah. Okay. So let's move ahead. I think this is enough. We can scale with this. Okay. I think we can get feedback. Okay. Perfect. Perfect. Shows a single Redis component, describes multiple horizontally. Now I have created multiple components. How would you handle node failures? Okay, adding details on how would be implemented would strengthen your design. Anyways, let's go to the next question. So next question is, what happens when our rate limiting fails? Okay, should we pass all traffic or block all traffic, and how do we recover quickly? Okay, what happens when our rate limiting fails? So basically, suppose if any particular Redis instance fails, we have two options, correct? Right, one is either we, you know, fail all the requests coming to that is which is, so fail all the requests uh, coming to that instance, right, which is basically we reject all the requests, reject all the incoming client requests. This would somewhere, you know, uh, lead the client to think that our API is down. Although this is not the scenario. You think, see, our API servers are working, but just because one of the Redis instances has failed, we are rejecting all the incoming client requests to that Redis instance. Okay. Anyways, another option is to allow all the, you know, requests coming to that. Allow all the incoming client requests. Again, this is also not a very feasible approach, because, you know, this might lead to DDoS attacks. You know, we might have malicious users trying to perform, you know, attacks on our system, and that would be allowed. Okay, so actually we have these two options, and how do we recover quickly? Actually, see, which one we should use, that would depend on the system. Okay, so uh, to pick one of these, uh, one of these failover, you know, scenarios, we will have to assess our system's requirements. Yeah. Because again, it depends, right? It would depend on a particular system, if we are, you know, if we would reject all the request or allow the request. Okay, anyways, how do we recover quickly? That I think is a better question. So whenever we have multiple, you know, whenever we have this threat or this issue or this, you know, disadvantage, where if a node fails, we have some issues coming up. So the ultimate and one single solution is we have to ensure replication of all the Redis instances, correct? Replication ensures high availability. This is a very important point. Like in distributed systems, if you have worked at your office or anywhere, you would know that we have to maintain high availability, we have replication. So we can have replicas, let's say 3 replicas, or let's say 2 replicas and 1 master per Redis instance. So basically, instead of 1 instance, we now have 3 instances. And if any master node fails, we try to, you know, what do they say? Promote the replica. So we need to ensure that the replicas are consistent with the master node. You know, we can have in-sync replicas, or, you know, maybe out of sync replicas. So we need to ensure that the in-sync replica is promoted to become the new master. we try to promote the replica to master. Okay. All right, I think this is a good enough solution that we are providing replicas. Let me get a feedback on this one. Okay, you currently identify the two main failure modes, fail open and fail closed. You recognize the importance of high availability through replication with a master replica setup for Redis instances. Okay. You didn't clearly state which failure mode you would choose for a specific system. Right, because I am unable to assess which one we should use. Actually, it depends, right? If we have something like, let's say, a social media platform, then we can go with fail closed, right? I mean, it won't be a disruption if someone is unable to add a post, correct? So it would depend actually on the system. Your recovery strategy focuses primarily on replication but lacks details on how to quickly recover beyond mentioning replica promotion. Okay, monitoring systems. Right. We can have monitoring systems that would, make it easier for us to figure out what is the, that our system has failed or something like that. So these are good points. A hybrid circuit breaker approach could be more effective than a binary fail open or fail closed. This would allow limited traffic between reset patterns when this is down. Okay. Let me just see the sample answer, what they're expecting us. Okay. So we can mention the replicas for failover. High availability starts with preventing failures in the first place. I'll run replicas with replicas and automatic failover. Okay. Gateway side, we need proper timeouts in circuit breakers. If Redis is slow or available, we can't let that anger gateways. So we need to decide on a failure mode. I would choose fail closed. Okay. If we fail open, okay, so fail closed is basically a better option as per them. If you want to get fancy, go beyond this. Okay. I think I will just add this failover replicas. Let me copy this stuff. Okay, and here I would say Redis replica. Replicas. Okay, so these are the replicas. I have to stay inside this box. So yeah, okay. Now let's move to the next question. How do we minimize latency overhead? Okay, so basically every call which we are sending, let me go to the test mode. So every client request goes to the Redis, or basically, performs a round trip to Redis, and a network round trip would take around 10 milliseconds. A network round trip takes around 10 milliseconds. This is very famous. If you try to go through the capacity estimation, you would understand this. Okay. So yeah, a network round trip takes around 10 milliseconds. So we want to minimize the latency overhead. Right. Because the scale we are looking at is 1 million requests per second. Okay. So one very important concept here is connection pooling. Okay, basically, suppose if we are, for every client request, if we are making a connection, let me just write also. So for every client request, if we create a connection, or let's say if we establish a TCP connection that would require, the TCP handshake overhead, and that is an overhead actually. Okay, so what we can opt for connection pooling. This is a very nice topic. You can read about it separately. Connection pooling. So you can go for connection pooling. So with connection pooling, what happens is, the API gateway can maintain a pool of persistent connections, and for the client request, they can reuse the same connections, persistent connections. This would allow client requests to reuse the same connections, right? And it would this will optimize the latency overhead. Other than that, other than that, latency would actually also depend on the the location of our servers, right? So obviously our servers should be close to the user's region, correct? Again, our servers should be deployed close to the client regions, right? We would have multiple regions and so multiple users. Other than that, I think this should be good. Let me see. I've not added anything, not changed anything on the diagram. You're on right track. Okay, currently under connection pooling, horizontally scaled. It takes around, but doesn't address how to meet the 5 millisecond latency requirement. Atomic operations, or if not, to combine multiple operations. Okay, so they're talking about request batching. Okay, that is a good approach. Other than that, while you have included Redis replicas, you didn't explicitly design for regional storage clusters, implementing it now. So let me see the sample answer. Sample answer, they have not changed anything in the diagram. To minimize latency, optimize every part of the path. Okay. So first, the call is from like gateways to the Redis. So creating new connections is adding significant handshake over it, right? So co-location is key in the same data center. Okay, right. This is a very important point which I've forgotten, that our gateways and Redis instances should be in the same data center. So it would keep the network latency under a millisecond. Cross region calls would add 50 to 100 millisecond, which is too much. For the rate limiting logic itself, I'll implement everything as a single Lua script, multiple round trips to Redis instead of separate get, calculate, set operations. Oh, right. Okay. This is a great answer, I think. For a global scale, we will deploy regional clusters. This is a great answer. We forgot two very important points. So yeah, we can take this into consideration. Let's move on to the next question. What is the next question? How do we handle dynamic rule configuration? How do we handle dynamic rule configuration? Where are rules stored, and how does our gateway know about them? Okay, so basically, where are rules stored? Okay, dynamic rule configuration basically means we have some user, basically how many requests a user gets per minute, but that would be dynamic, depending on if suppose we have some premium users. For the premium users, we can give them more requests per minute, correct? So we need to hold that. Okay. I think so we can store the rate limiting rules in a DB, let's say, and we can have workers which would pull the. So basically we have two ways. One is a pull based approach, another is a push based approach. So pull based is basically all right. So let's say that we are storing the rate limiting rules in another DB, okay, and we can cache the rules. We can also cache them, and we can cache the rules. Keep the rules cached, or let's say we can keep the rules cached. Okay. So one is that if the rules change, we push the changes. Basically, we push the changes to our middleware API gateway to inform it about that there are some changes done. Okay, another approach is the API gateway can pull the data from cache or DB. Now for pulling, we would have to implement polling, right? Polling. So the API gateway will need to continuously pull, continuously, I'm sorry, will need to consistently to pull the cache, pull the DB, let's say, every 30 seconds, or let's say even if we are pulling every 10 seconds, we might lose on the changes done for some amount of time. Okay, so the push based approach is a better solution, where if if the rules change, then we would push the changes to our API gateway. So what we can actually do is that to maintain the rules, let's say we have a DB. Let's say we have a DB, okay, and we have a cache. Okay, so from DB to cache, the rules are let's say, so workers, the rules, that's it. Okay, DB storing rate limiting rules. Okay, so you can go via this approach. Now to push the rules to gateway, we can have different approaches. We can use zookeeper to push the changes to the API gateway or something. So let's say what we can do is we can push the approach to our gateway using zookeeper. Okay, so we can do that. I think, yeah. Okay, great. Propose both solutions. We can do it for storing the casting layer to improve the performance. You recognize the limitations of polling, potential delays in propagation. Your whiteboard doesn't show zookeeper, which you mentioned, including would make your design more complete. View sample answer. Okay, so they have added zookeeper rules and something like the push. Okay. Okay, I think this is good. This is great. Okay, complete practice. I don't want to. Okay, I don't want this, but okay, we are done with the question, I think. Rate limiter. Hello, review. Yeah, I think we are done with the question. So yeah, before going through that question, I have gone through the LXU's blog, and I've gone through multiple resources online to understand rate limiter. Yes, for rate limiting algorithms, that I think that this this we can pick up in LND of rate limiter. That would be great, actually. So yeah, I think that's it. That's it. I think we are done with this. Right. So okay, we have clocked 1 hour, which means it is a good estimate for interviews. In interviews, we will have 1 hour only, not much, not less. So we need this much content for our system design. Yeah, I think that's good. I think we can stop here. Thanks all.